I think video sharing is now started.
Yes, it's working now.
Yeah, great.
Sorry about that. Yeah, I'm glad it's back. Yeah.
And she's saying something like crystal clear audio, even if the lingo isn't. Is that correct?
Video is also now coming through. I am able to turn on my camera.
Shall we get started then?
Yes, please.
All right. Good evening and a warm welcome to everyone here. Thank you for joining us today at the fourth webinar in the IRIS webinar series. Today's session on research initiative titled Critical Transitions in Complex Systems is led by Professor R.I. Sujit. It is my honor to welcome and introduce Professor Sujit. Professor Sujit graduated with his BTech in Aerospace Engineering from IIT Madras in 1988 with first rank. He received his MS and PhD from the Georgia Institute of Technology, where he received the top graduate student in the College of Engineering Award. He worked as a postdoctoral fellow at the Georgia Institute of Technology in 1995. He joined the Department of Aerospace Engineering at the Indian Institute of Technology, Madras in 1995 and is currently the D. Srinivasan Chair Professor. He is a recipient of the Alexander von Humboldt Fellowship and the Hans Fischer Senior Fellowship of the Institute of Advanced Study of the Technical University of Munich. Professor Sujit was the founding editor-in-chief of the International Journal of Spray and Combustion Dynamics from 2009 to 2015 and is currently a member of the editorial advisory board of CHAOS. He has won the Young Engineer Award of the Indian National Academy of Engineering. He has been awarded the Swarna Jayanti Fellowship and the J.C. Bose Fellowship by the Department of Science and Technology. He is a fellow of the Indian National Academy of Science and Technology. He is a fellow of the Indian National Academy of Engineering and the Indian Academy of Sciences and has been conferred the title of TUM Ambassador of the Technical University of Munich. Professor Sujit currently works on the application of dynamical systems and complex systems theory to study thermo-fluid phenomena. In his free time, he enjoys reading and learning and playing the guitar. Joining us today as the moderator for this session is Professor Maria Heckel. Professor Maria graduated in physics at the Technical University in Berlin and completed her PhD in 1985 on heat sources and acoustic resonators at the Engineering Department of the University of Cambridge. She is currently a professor of engineering mathematics in the School of Chemical and Physical Sciences of Kiel University. She has a total research grant income of over £10 million and have established around 100 articles in journals and conference proceedings and has a patent on reheat bus control. She was the president of the International Institute of Acoustics and Vibration. She currently serves on the editorial boards of the Journal of Sound and Vibration and of the International Journal of Spray and Combustion Dynamics. She is passionate about research that benefits the environment, as well as about gender balance in scientific research. Her research interest is in physical acoustics with technical applications, in particular noise control, instability control, and non-destructive testing. She has been the coordinator of many international projects. Professor Sujit and Professor Maria are currently collaborating on an European Commission project and has in the past collaborated in another European Commission project. We're very glad you could join us today, Professor Maria. Now over to you, Professor Sujit.
I will share my screen now. Just let me know if it's working. Are you able to see it, the screen in full
Yes,
screen?
we can. Yes.
Yes.
I can hide it somewhere in this. Okay. Good day, everybody. Before I start talking about critical transitions, I want to thank the organizers for giving me a chance to make this presentation. And I want to express my gratitude to Richu, who has been helping out with this grant. And I also want to thank many of my collaborators who are already here. In particular, I see Maria, who has been here to moderate the session. I also see Isaac Box. Thank you, Isaac, for coming. And I don't know who else is here. There seems to be a lot of attendees. So thank you very much for all for coming. So let me jump straight into it. Okay. So I get a chest pain and I am in great pain and I don't know, is it a heart attack or something is happening? But then also I'm wondering whether I ate something too much and is it just not a heart attack and nothing to worry, or is it just a heartburn? Well, I don't want to take the risk. So I take the phone, call 108 in India or 911. And then because, these are identical symptoms I can't make out. So I want to play it safe. So I've decided now it's probably something with my heart and I don't want to take a risk. So I call the ambulance and I rush myself to the hospital, and then the doctors see me and they say that, okay, dude, you didn't have heart attack. You just ate something too much and you didn't digest. And they give me some antacid, which costs very little. And they just send me back home. And I look like a fool in front of my family and the doctors and everybody. That's not the worst of it. I get a very big bill for the medical services and ambulance and all the things that I used and didn't use it and all that. And I complained to the insurance company. They say, if you died of heart attack, we would have paid you, but we are not going to pay you for having antacid and acid reflux. Okay, so this is one scenario, and the insurance is no way for acid reflux. Okay, so now imagine the other scenario. So I think, okay, it's just a heartburn, acid reflux, and I don't want to make a big deal out of it. So then I take the same antacid and go to sleep, but never to be woken up. I just rest in peace. And then my family has to deal with my body. So there are these kind of critical transitions and the cascading effects, not only in engineering and physics and so on, but in life as well. And any complex system undergoes critical transitions. So the system shifts abruptly from one state to another when the control parameters change past a critical point. And a slight change in the climate, for example, can lead to collapse of ecosystem, just as there are many other examples. The examples are all around us. So, for example, epileptic seizure is an example of a critical transition, and so is spontaneous asthma attacks and Arctic Sea melting. So these are all examples of critical transitions, or stock market crash, financial crisis. That's a critical transition. Or in thermoacoustic instability, you have large amplitude oscillations because of the feedback between heat release rate and the acoustic field in the combustor, leading to very large amplitude oscillations. And this is a very big problem in gas turbines and rockets. So in critical transitions are often undesirable or sometimes even catastrophic. And we also been seeing extreme weather and climate changes, and this is affecting the society very badly, causing death, injury, illness, trauma, and a lot of adverse socioeconomic impacts. So floods have been happening. In last 3 years, we had actually very severe floods in the west coast of India. At the same time, we are having droughts also at some other parts of the country. And this is some phenomena all over the world. Now we read that in northwest United States and in Canada, which is usually a cold place, but they're having extreme heat, I think close to 50 degrees centigrade, and the climate changes cause changes in extreme event frequency, intensity, and even the locations where this happens, geographic distribution has happened. And so in this project, we study critical transition and extreme events in flow systems and engineering, and also nature, using the framework of complex system theory. We will study 3 different transitions: transition in thermo-fluid machinery like rockets and jet engines or power plants. And we look at extreme events in climate systems and their cascading effects. And we'll also look at onset of precipitation in clouds. So the behavioral systems are often independent of the details and are driven by the interactions. Now, this is something which really disturbs people who are experts, because I'm expert in something and you say that you don't need to be so specialized that my system has something to do with some other system. That's sometimes my ego takes a big beat actually. But you look at the climate system where you have and you have all this very interesting climate phenomena. And we look at the a combustor where you have certain other interesting phenomena. There are so many things in common in climate, and they're driven by feedback. In climate system, you have ocean currents and wind. So that is the flows interacting with the heat release by the condensation of droplets in the clouds. In the combustor, you have feedback between the flow, which is in this case in the form of acoustic oscillations, and also the vertical fluctuations interacting with heat release rate fluctuations. And these interactions occur over an enormous range of scales, and they actually in different layers, actually different variables interacting with each other in another layer, and so on. And actually, in spite of the differences, they actually have a lot of commonalities actually. So I play these movies here. There's a flock of birds moving. There's a large number of interacting components, if you think of each bird, there are thousands of birds, but they're actually flying in a certain pattern, well-organized pattern. Likewise, on the right, I have the phase between pressure and heat in a combustor. Now, this is what decides whether the acoustic field is going to large amplitude and the oscillations are being driven. So you can see that there also it's a turbulent, very disordered system. And on the other hand, you have thousands of birds flying on the left side, and here there's a turbulent combustor on the right side. But there's an order emerging from chaos in both these systems. And we need to investigate the common features of critical transition. In fact, when I saw this movie first, that's when I got inspired to study this problem in great depth. Complex systems have a very large number of highly interconnected elements. So you can think of each of the element as a node, and there's a link between them, and then you can draw graphs or connect them. So these connections can be physical, like in the case of power grid or an airline network. For example, in the airline network, you have airports and you have flights, which are the connections. Okay, or in fluid mechanics or thermo-fluid systems, you don't have a direct, two nodes connected by links. So these are hidden or abstract, and these connections are multi-physics, multi-scale, and multi-layer. Okay, so there's so many phenomena happening, and so on. So in climate networks, we have multi-layers comprising wind velocity, temperature, precipitation, and cloud cover with interaction across different layers. Okay, so the complex networks actually help us unravel these hidden connectivities and help us track their evolution and obtain precursors to extreme events. So, for example, this is actually the complex network which I constructed for a thermoacoustic system. And you can actually unravel the hidden connectivities, although physically you don't see any nodes and so on, but you can actually unravel it. And you can track the evolution of these networks. And that's what helps us identify what is going to happen. So we need to obtain early warning signals and also have strategies to avoid or mitigate these transitions. And once you have the early warning, there are two things you can do. If it's a thermo-fluid system, engineering system, you can actually, maybe if there's a range of parameters where it's going to get into trouble, then you can avoid it. And if it's or if you still want to be at those parameters, you can have some mitigation strategies which are based on calculations. Or if it's a natural system, of course, you cannot avoid it because you have no control over the parameters, but then you'll have to mitigate using some mitigation strategies. Okay. So here we'll use a data-driven complex system approach supported by machine learning to map the evolution of the hidden patterns and connectivities. So we will use the frameworks of complex networks, fractals and multifractals, recurrence quantification, and framework of synchronization theory to be able to study this. And we'll use them in conjunction with artificial intelligence or machine learning, and to map the evolution of this, to unravel this hidden patterns and map their evolution. And so we will try to do coherent structure identification And then from that, we can model we can construct low order models based on the dynamics of these covalent structures. We can characterize extreme events. We can characterize regime changes and obtain early warning for them. And we can also make smart control strategies. So we have good experience in all these things in the past decade, actually. We have a number of well-instrumented rigs to study transitions in a fully turbulent thermo-fluid systems. And we have a swirl and a bluff body stabilized turbulent combustors with high Reynolds number, which are fully turbulent, and we can do particle image velocimetry, high-speed chemiluminescence, and acoustic pressure measurements, etc., simultaneously. And we need real high-quality data to be able to make theory. And we also have a turbulent combustor with preheated air, because the preheater changes the dynamics, and with that, the behavior is can be completely different. So we have that system, and we also have annular combustor, which is a very popular device in the power generation field as well as in the aero engine field, and we have that. We also have other systems like aeroacoustic, aeroelastic systems, but I think since time is short, I will skip that. Understanding thermo-fluid instability is a very complex phenomenon, and being able to do the control will require the application of the latest advances in complex system theory. This movie represents the complex dynamics. It's from my collaborator Isaac Box from DLR. And we have an international network of researchers working in laser diagnostics, computational fluid dynamics, simulations, and complex system theory, transcending boundaries between engineering, physics, and mathematics, because you can't solve them with one thing or one subject, because that's like looking at one part of an elephant. Like there's a story about 4 blind men looking at an elephant. Each one has a different picture of the elephant. One thinks that elephant is like a rope, another thing elephant is like a tube, another thinks elephant is like a pillar, and so on and so forth. But instead, we have to have a holistic, complex system view of these things, and we have to work together and transcend the boundaries between engineering, physics, and mathematics. And one person, one group cannot do it. And we actually have a very big group. We also have made a laboratory experiment. We can have the cloud in the lab. Cloud formation happens and how precipitation happens. We made a turbulence chamber to study this in the lab. And sorry, for the weather, we have the various data sources. First, we will be using satellite-based data to construct the climate networks and study the extreme events and the climate dynamics. And we have established a network of leading experts across disciplines. And I'm really fortunate to say that we're really fortunate to have really good people, very good people, top in the field, collaborating with us. And we really need people across the disciplines, and we collaborate to solve really complex problems, not model problems or anything, but the real thing. And the technologies that we develop can be used directly in the industrial systems. And we have a combination of dynamical systems people, complex system people, combustion people, turbulence, thermo-fluid dynamics people, acoustic people like Maria here, and propulsion, mathematical biologists, power grid dynamics, climate dynamics, and global collaboration, transcending disciplines and transcending borders is required to tackle problems of this magnitude. And we have been collaborating with these people for the last decade or so. Many of them, some of them in the last 4 or 5 years, some of them even longer. We try to unravel the science behind these transitions in diverse systems and develop trained human resources and translational technologies. So we develop tools for early warning of critical transitions and extreme events, and we mitigate transitions and their effects through smart control actions. And these tools that we develop, we take our inventions to the market, to the field by having startups, and we will have product development and startup incubation, and we'll develop an online international education and technology dissemination program through webinars and short-term or international courses and so on and so forth. And in the short term, that is in 2 years or so, the project is in 2 phases. So in the short term, we develop tools to predict, avoid, and mitigate instabilities in thermo-fluid system. This instabilities in thermo-fluid system has been a showstopper for the development of aero engines or power plants and ship engines, rockets, and so on. So this would be the short-term impact. We'll be able to contribute towards ensuring energy security, which is a big thing now, national security and access to space. And we will, India's economy dependent heavily on monsoon, Indian summer monsoon. And a typical monsoon has a very big cascading effect, causing extreme events and so on. So we'll develop predictive model for a typical Indian monsoon and the ensuing extreme events and obtain local and global precursors with which once you know something is going to happen, first of all, we would want to know if the monsoon is going to be a typical well in advance, and if other local extreme events that's going to happen. This would be our contribution in a time span of 5 years or so. And in the long term, we would provide guidelines for sustainable development, accounting for the increased variability in weather patterns, because the climate change is a big thing. And currently the losses are estimated to be like 8 trillion or so. And the estimate vary in the next 20, 30 years, the losses, economic losses to the global economy due to climate change is going to be estimated between 20 to 50 trillion. Actually, there's a very big thing, and it's very important to be able to provide guidelines for sustainable development, accounting for this increased variability in weather patterns. And in the long term, we'll establish technologies that enable critical interventions. For example, if there's a forest fire, where do you put a fire break? Or if there is a pandemic, when do you implement lockdown? And we would generate transdisciplinary insights and provide the society and the government with sound information for decision making. Thank you. I'll be happy to answer your questions.
Thank you very much, Sujit, for a very impressive, informative, and entertaining talk. As Sujit has said, he's happy to answer questions. So if anybody has any question, please speak up.
I think they are on the chat box. Perhaps you can select them.
Okay.
Q&A chat box, you can see questions from the participants. At the bottom of the screen, you have a Q&A box with about a couple of questions.
Is this in reverse order? So I have a whole list of questions.
We can pick some and ask them.
So let me pick a good one. And it's changing. Yeah, let me go for this one. Please tell us more about online education in this subject. That's a very interesting question and sort of related to outreach.
Okay, so we are planning a series of online webinars with the best speakers in the subject. That is one thing we are going to do. Then the other one is conferences, and there will be physical conferences like the one you and I are going to do once this pandemic is over. That is this Indo-European meeting in Chennai. And then we'll also have virtual workshops where we have experts all over the world, and the participants can also stay at their home and do this. So we are going to have a host of things where we have this online education programs.
Okay, thank you for that, Sujit. And another question is, can industrial companies participate in your project?
Yeah, definitely. I think there are many companies who are already working with us for the last many years, 10 years or several years. And I'd be happy to, you can contact me and I'll be very happy to talk to them. You can definitely take part, and we look forward to support. And I think all this is done for the industry. So definitely, yeah. And so okay. It's very strong, yes.
Great. I'm reading out the very last question now. It says, very exciting presentation. Yes, I fully agree. How many of these ideas have been implemented in engineered systems already? And what is the prediction for applications in the next few years?
Yeah, actually, we have developed precursors for thermoacoustic instability, aeroacoustic instability, aeroelastic instability, etc. That is the oscillatory instabilities in turbulent systems. We have a large number of patents, and they've been implemented. They've been implemented on the field, as in gas turbines and rockets. And we also have some patents jointly with Potsdam, with Professor Kurtz and Norbert Marvel on critical interventions. So find out which regions where you can manipulate so that we can have a smart passive control. So we have a number of ideas which have been implemented actually, and some in the gas turbine and the rocket. And I think climate interventions, we are relatively new to the subject, but there are other people who have made inventions on that. So the idea is to be able to make predictions of extreme events or something like big floods coming or so on, and to get precursors, and then also predict the cascading events and so on. So that we think in 5 years we'll be able to do that together. And we are planning to, of course, we'll work with, if some companies are interested, we're also planning to have startups to incubate our products. We have some products we are building on. Maybe in a few years, it'll be there. Well, maybe in a year and a half or so. Yeah.
Okay. Here's another question. How can these predictive models be implemented for scramjet propulsion and its development?
Oh, I have not quite worked on scramjet engines.
It's very technical.
But this complex system approach should be the whole thing behind complex system approach is that if you have data, we can unravel the connectivities and the dynamics and can construct the model. So I think for scramjet, my suggestion would be that we take high quality optical diagnostics data and or obtain high resolution LES, high multi-fidelity LES data. And with these, we can apply the complex system theory, and then we can unravel the hidden connectivities and detect the structures and construct low order models. So that would be the thing. I have myself never worked on scramjets. I worked on gas turbine engines myself and rockets, but this is what I would do if I were to work on a scramjet engine. But it's data driven, but then you try to get a lot out of data than just plot it and see.
Okay, thank you. And there are a couple of questions asking for a relationship with electrical engineering, if you work with electrical engineering.
Yeah, so I think power grid dynamics is a very important thing, and many of these phenomena happen in power grid. The stability of power grid, something very similar to this instability in thermoacoustic system, and also some of the things that we studied like rate dependent transition in thermal system, same thing is there in power grid dynamics. So power grid dynamics is one place where this, which I know I've read papers on, and some of my past students have gone, and Gopal Krishnan has recently written a paper on power, and together with Elena Siravatkina, they have written a paper on power grid dynamics. I think that's someplace this is definitely useful. I don't know much about electrical engineering, but I definitely know that this is a subject where it can be. Now, other thing is Internet of Things, and also Internet of Battle things. So I think those are places where complex system theory will play a big role.
Right, thank you very much. I'm struggling here because the questions keep jumping around, so please bear with me. There was oh yes, can you give examples of smart technologies developed by studying critical transitions?
Yeah, I think this iWatch, I don't have one, but that is something where it predicts whether your health, whether you will have a heart attack or not. And that's one example. The same thing long time back, maybe 2000, before 2010, Toyota had instrumented their cars, steering wheels with sensors, which when you hold the steering and before you crank the car, it will sense, it will give a quickly download the data and check whether you're going to, how healthy is your heart. Because in Japan, a lot of people die in the road getting heart attack. Japanese are quite stressed, as you can imagine. They work very hard. So if the car senses that, the computer senses if you're going to get a heart attack, now they can predict this as early as 4 days actually. So if it's like more than 2 days, they are going to let you, they will tell you to drive to a hospital. But if it's less than that, they would not let you crank the computer will not let you crank the engine, but instead it will call an ambulance and ambulance will come to you. So that's a very good example. I think this was there even before iWatch came. iWatch is one example. So engine health monitoring is another example where this could be more. So epilepsy can be detected in advance, just like heart attack, and also migraine attacks. So there are a whole bunch of places where critical transition can be used. And I was at a conference last year where I met this doctor. I don't quite remember, maybe his name was Weber. And they were actually finding the, he was a surgeon, but at the same time, he is a PhD in complex system theory. So they ablate some of the heart tissues for some problems. And they find out using this complex system theory analysis, which is the critical region, and they actually ablate that. So I think the medicine is one place where complex system theory is very advanced.
Okay, thank you for that. Can I ask you a question and make a comment?
Absolutely.
So your applications are extremely diverse, ranging from thermoacoustics to medicine to climate and beyond. And it's all under the umbrella of complex systems. Right. And I suppose what's linking all these things is the mathematics. Do I see this correctly?
Yeah, I think the whole thing is that independent of the physics of the problem, the systems which have different physics, they undergo the same behavior. So I think this first came into light when in this work of Kadanow and Wilson, where they show critical scaling and V-down scaling before critical point, where you actually found that phase change in completely different systems. For example, crystal structure changing or ferromagnetism becoming paramagnetism. You had certain thermodynamic parameters diverge of specific heat, conductivity, heat capacity, all those things change in a certain exactly same way in different physical systems. Now then, so Nobel Prize went to Wilson. And then in the 70s, I think there was this great work by Haken and also by Prigogine on non-equilibrium systems, the same kind of thing. And what Prigogine actually got Nobel Prize. So systems which are hugely different, they actually surprisingly near the critical transition, they have the same behavior. And so the key thing is that the details of the thing are not that important near the critical transition. It is the connections, and there seems to be like a universal pattern or to a certain class of systems. So in equilibrium thermodynamics, this is really universal, but in non-equilibrium thermodynamics, like the combustion instability and so on, this is more like for certain class of systems, there is a common behavior. And the mathematics is, like you pointed out, it is the same for every system. Actually. And tools from one, it's just that in each subject, one maths, for example, climate dynamics had this complex network being applied to climate networks. And we use that now in thermodynamics. Now we learn more, we put it back in climate network. So there is this underlying beauty of this subject. Yeah.
Absolutely. I would say it is beautiful, the sort of the connections between the different subjects, vastly different subjects, and also the connections between the different research groups all over the world working towards understanding these things.
Yeah. We have been really fortunate to work with. I showed you some of the pictures of my collaborators, there's more. And we have been working in the last many years, which is the only reason we are able to succeed, because you cannot do it alone, and you really need a expertise is there all over the place. Thermoacoustics in UK, great quality data in Germany, DLR, some other things in Canada, some other things in the United States. So we are collaborators all over the place, and they're all interested in this critical transition. Each one will call it different name.
Yes. How much more time do we have?
You have to ask Richard.
Officially, we have 15 minutes more, but the meeting can continue. You can take on as many questions as you would like.
There is no presentation after this. So
we do not have a hard stop, and we don't have any webinars after this. So
okay, good. So thank you very much for answering my questions, Suchit. So I will return to the chat box and read out a few more of the questions that are in there.
Professor Elena, Professor Maria, if you could look at the top of the chat box, it has some of the upvoted questions. So if you think some of them are good, they could be answered.
Okay.
And
I could read out the questions for you, and between both of you, you can choose to answer. Shall we do that?
Okay. Yes.
Okay, so the first question is, as per the slides, the data are shown collectively. How can we find information from exact point of location? Professor Sujit, perhaps you can take that, or his network is down.
I'm not sure if the question is clear enough, because we do not know which slide it was referring to.
It's difficult, this one, to answer.
Oh, I'll take another question. Can somehow cloud moment can be made a oscillatory kind by balance between non-linearity and dispersion? In short, is there a way to make non-integrable moment of cloud into integrable one?
Wow, very specialist question. The honest answer is I don't know.
Okay, maybe we'll take some.
Do you have an answer to that?
Okay, so there's one question. So a career in combustion or a career in data science, what's your suggestion?
Both. I mean, these are both very timely subjects, and I expect a lot of new developments in the foreseeable future. So I think they're both very promising subjects.
And can you please give us a few details at a high level for the type of AI ML models used in these kinds of systems?
AML. What's AML models? Sorry.
AI, artificial intelligence and machine learning, AI and ML models.
Sorry, the internet went off and now I am tethering from my mobile phone.
Okay, I think Sujit, you are in a much better position to answer this question.
Yes, we can see you.
Okay, let me look at the screen and I will see from where it stopped.
So there's one question on, how would this impact the circular economy?
What economy?
The circular economy.
Oh, I don't know.
Sustainability. Okay. And there was a question about the use of AI and ML models.
Yeah, I think AI is very good at dealing with complex system. And what we're trying to do is to use various things with AI, but actually we think there's a lot to gain by using physics-inspired machine learning. That's what we're using, and we had good success. Some papers are under review, and we have also filed some patents. So I think we are going for physics-inspired AI. We are not primarily physics people, but primarily AI people, but physics-inspired AI has given us a lot of success actually.
And how does thermoacoustic instability connect with climate change?
Actually, climate change is a bit difficult thing to study because whatever happens, happens. Whereas in thermoacoustic instability, you can actually make the experiment anytime you want, as many times as you want. And so it's a very, and the models, the complex system tools from complex system theory are same, and there are so many common features. So if you can, I think thermoacoustic system is a good platform to get the complex system tools running and really push it to the level best. And then you can use that to study climate theory. So it's like an indirect route, but I think it's very good.
Can you provide some good resources or books on complex systems which also cover critical transitions?
Yeah, I think there are plenty of books. If you go to even Amazon and click complex system, you would see lots of books. I don't have anything specific to.
Do any of these cover critical transitions? I think that's the point.
Yeah, I think there are a lot of things cover critical transitions. And the simplest book I would say is the book by Scheffer, SCHEFFER, on critical transitions. Critical transitions and complexes. I think that's a good book, Scheffer. Simple and very nice book.
what is this your favorite? And if not, what is your favorite book on complex systems, Sujit?
I think Schaeffer's book is a very good book, and Harkin's books are very good. So is Prigogine. Prigogine writes very nicely. These books are old, but Schaeffer is very relatively new book. And for complex networks, the best book I would say is Barabasi has written a book on network science. So, and if you want something popular to read, Barabasi has also written a book called Linked, which is like a bedside reading. But the complexity science is a very good textbook actually. And I think there's one by Newman also, which is very nice. Now there are a lot of books actually.
So Professor Maria, we're very cognizant of your time. So if you are, if you have other engagements, you're free to leave. So the formal webinar as such is over. But if Professor Sujit would like, we're happy to have him for some more time answering questions. So it's entirely up to you. So we can continue with
I'll be happy to see.
Yeah.
And sure. I say question, can we predict a critical transition? We can indeed predict critical transitions. Lots of ways of predicting critical transitions. So it's most of the predictions are data driven, either using machine learning or physics based. Where do I get a Zoom recording? I think the same link, if you click, it will play. How can we implement electronics and communication engineering? These tools are very general. There's nothing that binds it to aerospace engineering or physics or anything. You can definitely use it in electronics and communication. I don't know.
There's another question here that says, could you solve multi-physics problems? Is it possible to have accurate predictions of combustion instability in turbojet engine?
Right. Yeah, it is definitely possible, and we are being able to forecast instability. And also for the spatial temporal dynamics, so far we have been using single layer calculations, but with multi-layer calculations, which we are doing now, it would be possible to do even better. And then there's a question, why synchronization source to predict extreme events? I think this thing is disappearing. Of a nonlinear phenomena should exist. If it exists, I think many times the interaction between different subsystems, which is what is causing synchronization. Sometimes, in some cases, the amplitude will go very high. So I think it definitely plays a role. Is there a future for experimental combustion, say 20 years from now? Can you advise from a career point of view? So I think long-term forecast is a very dangerous thing to do. So I don't know. I mean, 20 years is too long to make predictions. But I think combustion is not going to. When I was in high school, they said that there was oil crisis in 1970s and Jimmy Carter's time. And they said that in another 10, 15 years, we'll stop the dependency on oil and so on, and renewable sources, blah, blah, blah will come. But it's now 50 years since then. I am old, 55 years old, and still we are using oil. So I think it has not gone away. Then if we could solve a multi-physics problem, yes, I think you can solve multi-physics problem. We have solved some of them. Do you think the science of early warning signals have good future? Definitely. I think early warning signals have a very, very good future, because I mean, the world is becoming more and more uncertain, and that's when you have either JRF program for PhD. Yeah, I think the data science is in many departments. You can do JRF if you could.
There's another question here. Can you please elaborate how you can predict forest fire?
Yeah, I think it's from satellite imagery that people do this, and it's not. It's what I was talking about. Maybe that's what they're referring to, is to find out where is the how to control the forest fire. So you can, from the satellite maps, you can actually find the path of the fire, and we actually have to make these control measures at the place where the centrality measures are very high. So there's something called, for example, between the centrality. So how central is a point to everything else? So then if you implement this control measure at the centrality point, that you cut down the trees or burn the trees in a region, then the fire cannot spread everywhere. So that is how complex systems theory would help. What are tipping points and bifurcations? Bifurcation is one type of tipping. The other types of tipping, for example, noise-induced tipping, which is noise can kick the system to another state, or there's rate-dependent bifurcation, or tipping, where you tip to a alternate state. There's at the low speed, if you change the parameter, you don't tip, but at a very high speed, if you go, the rate of change of parameter itself becomes a parameter and can tip. What is the software that can be used to model complex systems? That is really a general question. I don't have an answer. What are the key takeaways for the data scientists in the industry? Please elaborate on such scenarios. Data science is very good, but you should also need to know domain knowledge, because without knowing what you're dealing with, you cannot make predictions, or predictions won't make sense. So I think it would be very good to know also what you are studying. How much focus on this thing just jumps up and down. I think I answered these questions. So maybe I should go to the top and see. How is it going to help farmers? I think that's a very beautiful question. So I think the farmers heavily depend on the weather. So if we can predict that the monsoon is anomalous, I think that'll be very good help. And if we can predict extreme rain, then if you know something is coming, sometimes you cannot do anything about it, but you know that extreme flood is going to happen, and then they are waiting to harvest next week, but then maybe they'll advance it. So there is, I think knowing the weather definitely help the farmers, and we can forecast extreme events based on satellite data. How does it explain instability in a thermoacoustic system? Thermoacoustic system can be explained in a laminar system, very simple way as feedback. But the thing is, we are in industrial combustors, we are having turbulent systems, and you have the turbulent system is the stable state. So the stable state is not silent. So the classical idea that you go with a Hopf bifurcation, you go from stable, from a fixed point to a limit cycle, that is not quite applicable, because we have chaos to begin with at the stable state. So we are transitioning from chaos via intermittency to order. So that's what happens in a turbulent combustor. Have critical transition models been applied in social engineering and prediction of demographics? I think there's lots of books on and papers on how critical transition happens in social engineering, about the spread of information, rumors, and so on, and even spread of coronavirus and so on. That's really complex system theory, and complex network has been used. And eigenvalues predict the transition from non-synchronization to synchronization in the linearized way. Yes, non-linear prediction, where if it causes the linear solution not to be valid, that's a possibility. I don't know how much more time I have, Richu, but I can go on and on.
You can go on. There's whenever you want to stop, we can stop.
Drink some water. If I want to do PhD in part-time RS and GAs in IIT Madras. Okay, so such specific questions you'll have to contact me directly. Tools in industrial ecology. Yeah, there are a lot. I am not an ecologist, but I have read a lot of things from ecology to be able to copy those things to thermoacoustics. And
there's a question here that asks complex systems. Would complex system method help in predicting sudden surge in rainfall and other?
Yeah, it does. It does. There has been, in the last few years, there has been quite a bit of work on this precipitation network. We are ourselves working on it, and yes, it is definitely. And they also predicted early warnings, etc., based on this.
On early warnings, there's a question of, do you think the science of early warning signals have good future in complexity research?
Oh, absolutely. It's very good future, because as long as the world is messed up and having chaos, I think if world didn't change and everybody woke up every day peacefully and everybody lived very happily and everybody lived till the age of 110 and died slowly, then there's no problem. But you have heart attacks, you have extreme rain, you have extreme forest fire, atypical monsoon, all these things. So this is what makes it keeps us in business. how can we get signs of extreme events in stock market? This is a very well-developed subject. I would like you to, I would refer you to the book by Didier Sornet on how stock markets crash. This is written very nicely. It's easily accessible, but at the same time, it's quite deep also. Didier Sornet, S-O-R-N-E-T-T. I think he's a Swiss scientist. Can you suggest books to learn combustion instabilities, especially in solid rocket motors? Surely, I have sent a book to publisher, so it will come out maybe in 2 months by me, so you can buy that. Okay? It talks about combustion instability.
The phase transition of a solid to a liquid or a liquid to a gas, etc., can it be described as a chaotic process?
I think this phase transition from solid to liquid or liquid to gas, they are equilibrium process. So I think it is better. You can use some of the tools here and the analogies, but it's not really a dynamic phenomenon. It is like it's an equilibrium process. So this is a nonlinear version of that.
Thank you, Professor Maria, for joining us. She's had to leave, but Professor Sujit, you are welcome to continue.
Okay, thank you, Maria. Yeah, I think very kind of you to come.
There's a question here, how to formulate complex variational pattern to reduce risk?
Yeah, I think people are working on it, but I am really not knowledgeable about this. I see on the question which I can answer. I am really not a risk analysis, but people work on this. What are the predictive tools and sensors that you develop to forewarn the thermo-acoustic instability? We have a patented algorithm and tool called Ether, early warning for thermo-acoustic systems. So it has a number of methods, a number of patents behind it. So we can get significant early warning compared to the event actually. So it's our software is called Ether. If you're interested, you can contact me, any of you. And lost this, things are rapidly coming and disappearing. What type of research titles can be formulated for the new areas and issues, and what your suggestion is? So those are very generic questions. So I think you could contact me and maybe we can have a more detailed discussion. And references to dynamic transitions and applications, there are plenty. So if you'll have to be a bit more specific than that. Will there be a webinar in Hindi? I don't have any problem, but you may not like my Hindi very well, but I'm sorry. Yeah, but it is definitely possible. I can speak in Hindi, but I don't know it very well. You may not be able to tolerate my speaking, but I'll be happy to speak to you in Hindi. You could contact me directly. Then how this transition work in the case of power grids? Yeah, power grids need stability and lots of stability, I think, and synchronization is a very important thing. And actually, this cascading effect, many of the blackouts, blackouts happened in Northeast some years back, and also in the United States and so on. So I think there are this cascading effects. That is what it is. And there's some hubs are there which are very critical, and if they go down, then the whole thing network can go down. How much focus and scope does multi-phase turbulence modeling hold since transition systems are highly phase dependent? I think it's a very important subject, and as long as people burn things and have sprays and so on, multi-phase turbulence is a very important subject. Does the boundary start on the split? I didn't understand some of the questions. Sorry. How to get data for complex network with varied parameter? I guess there's no easy way other than to do experiments, but people also do simulations. And for example, for physiology, you could actually get signals from. There is a network called PhysioNet, and where we can download. My students do that, and it's freely available, and you can actually get, for example, data for heart attack and so on and so forth. What is software? I think there's no general answer you can use. I think I have kind of, can you employ complex systems models to preventing calamities instead of predicting it? Yes. So not only can you predict calamity, you can also suggest measures which we can employ to be able to stop this transition. So you can find measures to manage. For example, maybe if there is a heavy rain like in 2018 happened in Kerala, then maybe if you know in advance, dam opening could have been, it could be managed through dams and so on. So always it's suggesting.
There's a question here. What are the data collection tools suggested for critical transitions? Should we have strong background in statistics?
I think background in statistics help, but yeah, I mean, you have to have some background in the subject in which you're collecting data. That would be good. If not, collaborate with someone who is doing that subject, so that I think on just a black box approach, I'm not really fond of it. So study something about the system and then collect data. How do yeah, there is this question about particular latitude and longitude. The satellite data comes with latitude and longitude, and different data have different resolutions. Some have 0.1 degree latitude, longitude resolution. Some has 2.5 degrees. So you can, it comes that way. The many data sets like IMERGE, ERA5, GPCC, they come with that. Okay. Any other question that I missed?
There's one here that asks, how can complex critical transitions like the duck curve formed by renewable power interaction and conventional electric grid be minimized, predicting electricity demand with generation?
I really don't know those technical terms because I don't work in power grid dynamics, but I know for sure that complex networks are used to study this. And there's one question, is there a general theory which encompasses different complex systems? That is the whole beauty about complex system. The theory is the same for every system. Can you tell us about some widely different systems that have same behavior during critical transition? This is a very nice question. So we have been doing experiments in thermoacoustic system, aeroelastic system, aeroacoustic system, and also in things like Chua circuit and random laser and so on. All of them behave on scaling behavior. All of the power spectra and the amplitude scale with the moments of the certain measure based on the moments, and all of them had a same exponent -3/5. And then various turbulent flow systems like aeroacoustics, aeroelastic, thermoacoustic, they all had a amplitude scale like 1/Hz exponent squared, inverse power law. So I think there are these are two examples I wish to give. And Ritu, have I missed anything else?
No, I think you've taken a lot of questions.
Cluster system and dynamics. I think there's a big thing in complex network. So I think I cannot give a simple answer, but finding cluster is a very big thing in complex network theory, and then predicting its dynamics and modeling. I think it's a very important.
We can take one more question and.
I see a nice question. How can you apply complex system theory to pandemic spread more effectively and control spread of disease and perform better compact strategies? So this, I think in 2013, there was this paper from these people in Berlin. I can't recall their names. And this was well before the coronavirus. They had made a theory based on complex networks for pandemic spreading. And the problem is that you can suggest measures, and whether those measures are implemented and how disciplined the population is there and so on. So some countries followed those science very well, and I think those countries you can see have relatively taken lesser hits. So I think it's definitely possible, and people are already doing it, and they've been doing it even before the coronavirus came. These predictions have been very good. I think, is that enough? Questions? I'm not able to. Are there any questions? Yeah, okay. If there are any questions that I missed, you can ask. I have more stamina, so.
Maybe you can take another 2 more and then we can wrap up.
Has the aviation industry started implementing a patented working on criticality on the electrical market? Aviation industry, I have tried out with aviation industry data, but it is, I don't know if it's there in any of the engines, these things actually implemented. I don't know, because aviation industry, it's hard to know, but definitely it has been implemented in some companies. I cannot tell more details. Also, electric cars. Do you think complex designs will remain? Yeah, I think so. Complex designs will become even more significant once cars are self-driven and so on. So definitely. Could you provide us with a real-life example that is detected with complex? Oh, I think this impending epilepsy attack or heart attack, that would be a very good real-life example. Yeah, can machine learning be used to solve climate change problems? Yes. Can complex system be approximated by simple system in mathematical modeling? I would say the complexity means large degrees of freedom interacting. The relative maths has been simple. So it's the connection that is important. And you don't have to go deeper and deeper. That is, reductionist approach splits the thing and writes detailed model about everything. Here the focus is on the interactions. What is the role of acoustics in boiling? I think maybe this is important if you're talking about sonoluminescence and so on. I think where the temperatures can reach very high values by the shock heating. So I think sonoluminescence is where you should look. How can SOM behavior help us understand more about thermoacoustic instability? Yes, because it is collective interaction, and thermoacoustic instability also collective interaction happens, and that's how this large coherent structure is formed, and a large amplitude acoustic field is formed. So I think it's very useful. How do we transition in data science? Oh, I think we'll have to put in the hard work and study. Then can you predict the future of combustion using complex systems? That I think it's I don't know about future of combustion. Maybe there are people who are modeling what happened. I think social scientists must be modeling. How do we predict critical transition in a multi-scale dynamical systems? I think there is multi-scale networks. The people at Potsdam, they have done very good work on this, and also multi-layer network, and then there's multi-layer, multi-scale. So that's the way to go. How to manage natural, and the question disappeared.
We can wind up now, sir.
Okay.
All right. So on behalf of all of the participants and the Office of Global Engagement, we're very happy that you could join us here. Your slides were very entertaining and informative, and you've answered so many of the participant questions. I'm sure everybody is super happy to have had this time with you. So thank you so much, sir. Thank you to all of the participants for joining us. Good night and take care. Thank you. Thank you, everyone.
Thank you. Bye. Bye, everybody. Thank you, Richard.
Thank you. Thank you, Rasa Sujit.
I guess you could close the meeting.
Yeah, we will. Thank you. Thank you, sir.